Hello and welcome to Math 253, Calculus 3 here at Cañada College. My name is Lapuz. In this video, we will take a look at a problem similar to a homework problem from Chapter 4, and this is section 4. I believe it's 4.6, when they're talking about directional derivatives and gradients. The question is to find an equation for the tangent plane to the surface z is equal to 5, or z plus 5 equals x times y to the 6 times cosine z at a particular point, 0.510. Now this surface is an implicit function, z is an implicit function of x and y. And so what we want to do is we want to, well, first of all, remind ourselves of a particular fact that will be important for us. And that fact is saying that gradients are perpendicular to level surfaces. They're generally perpendicular to level curves or level sets, to be the most general. But in this case, if we take a look at this as a surface, we can recreate this as a function of 3 variables, and we can find the level surface of that. All right? And what we're going to do is once we define that function of 3 variables, we're going to look for its gradient, evaluate it at this point, and then we will have a vector that is perpendicular to the level surface, and that will give us our normal vector. And we'll use this point to create our tangent plane. So just as an aside, remember for a tangent plane or any plane, we need a point and a normal. Okay, we have the point, that's done. The normal vector will be the gradient. The gradient of what? Well, again, we have to look at this surface as if it was a function of 3 variables and equal to a constant. So we could do this in a couple of different ways. I prefer to solve for the whole thing and set the whole thing equal to 0. So I mean solve, I mean bring everything to one side. So let me write x times y to the 6 times cosine of z minus z minus 5 is equal to 0. Okay, so now this is the exact same surface as what's given to us, except now it is equal to a constant, and we can focus on just this part, the left side of the equation, and call that a function of x, y, and z. So we can say that f of x, y, z is equal to x, y to the 6th times cosine of z minus z minus 5. And this is the function that we're working with. Now, we know that if we let a function of x, y, and z equal to a constant, and 0 is a constant, then this is actually a surface. And not only is it a surface, it's actually a level surface of that original function f of x, y. And because it is, in fact, a surface, then we can find tangent planes to it, and we'll use this fact that the gradient is perpendicular to a level surface where we can find the normal vector. From here, we just have to find the gradient. And to find the gradient, we need to find the partial derivatives of x, y, and z. So let's start with fx, the derivative with respect to x. We will treat y to the 6 cosine z as constants, and the derivative of x is just 1, so that's y to the 6 cosine z. And then these two terms, the z and the 5, will be 0 if we take the derivative with respect to x. We will be interested in putting in 510 as well, so let's do that now. F sub x of 5, 1, 0 will end up equaling to, let's see, there's no x's to put 5 in, y is equal to 1, and z is equal to 0. And I think this will give us a 1. All right, moving on, we'll find the derivative with respect to y. This time y is constant, so that would be a 6y to the 5th. And x is a constant, and z is a constant, so cosine z will remain the same. And the derivative with respect to y of z minus 5 or minus z minus 5 will be 0 again. And so we want to put in 510 into the equation or into the function. We're going to put 5 in for x, 1 in for y, and 0 in for z. And it looks like we will get 30. And then fz, the derivative with respect to z. So the derivative of cosine of something is negative sine of that something. And so I will have a negative. Xy to the 6 will be constant. The derivative of cosine is sine, and that negative is already out here. The derivative of z is 1, and then the derivative of negative 5 is 0. So this is our derivative with respect to z, and now let's evaluate at 510. I get a negative 5 in for x, 1 in for y, and sine of 0 is equal to 0. So this first term will be equal to 0, and you just have negative 1. All right, so our gradient vector evaluated, let's evaluate it already at 510, is going to be equal to negative or positive 1 for the first slot, 30 for the second slot, and negative 1 for the last slot. So that will end up being our normal vector. Okay, so we have a point, 510, given to us at the beginning of the problem, and then now we have a normal vector. So to find our equation of the plane, if you remember, it's just the normal dotted with the x, y, z. So 1x plus 30y minus 1z is equal to, and then we take the dot product. This is our d, the dot product, 1 times 5 plus 30 times 1 plus negative 1 times 0. So that gives us 35, and that is our d. So our equation is going to be x plus 30y minus z is equal to 35. Okay, now we do have the tools to look at this in a little bit more detail, and so let's take advantage of our CalcPlot3D graphing program. And I got things started already by putting in an implicit surface. So an implicit surface is a surface that is defined by an equation, so something with an equal sign, and that contains x, y, and z, x, y, and or z, depending on the combinations. And then I throw in this point as well, the 510. All right, so looking at it from here, it looks like we need to zoom out a little bit because 510 is all the way over here. So let's zoom out. And you can see that point is not yet on the surface. Let's zoom out one more time or one more level. You can see that it clearly does not pass the vertical line test. And that's why it's not a function. You can't, I mean, you can solve z is equal to something, but it's going to be really hard because there is a cosine z in it. In any case, you can see that it doesn't pass the vertical line test, so it's not a function. But if you focus on this one spot where the point is, you can see that at that one spot, we can imagine that it's going to be a function there and be able to find things like tangent planes. All right, let's make this just a little bit more transparent, and let us get rid of the lines, and let's make this a little bit finer. It'll probably slow down the rendering, so it'll be harder to take a look at it from different points of views. But here's your point. Maybe 32 is a little bit too much. Let's go 24. Okay, my computer is slowing down already quite a bit. So it's going slow, but it's moving, and you can see that graph, that point. Now our vector, that is our perpendicular or the normal vector, is a really flat vector. And that's 1, 30, negative 1. So let's draw that. I don't know if it's worth drawing, but let's draw that. It'd be 1, 30, negative 1. And this vector is really going way out there, and it doesn't look like it'll help us unless we put it in the right spot. So let's have its tail initial point start at the point that we're at, which is 510. And it looks like that is fairly normal to the surface. Let's see, we can try to zoom in a little bit and see that it is. It looks like it could be normal to the surface. But let's be more interested in finding the plane, or graphing the plane to see if it's there. So I'll do the plane as an implicit surface, and it was x plus 30y minus z is equal to 35, I think was the d that we found. And let's go ahead and graph that. And we hope to see a plane that would be tangent to the surface. All right. There it is. It's kind of hard to see. Maybe we reverse the colors so that it'll look different from the original graph. And then make it slightly transparent. You can see, it's hard to see, but you can see that it looks like it is tangent at that point. All right. It is almost like a vertical plane because of the y having such a large value. But I think that's it. All right, I hope that helps. And that's it. Good luck.